So today we'll be discussing about the aspects of thermal state of a quantum field. Remember, we started our discussion in this subsection regarding three important classes of states. One was the vacuum state, which we have discussed about. In the previous discussion session, we covered the aspects of coherent state. And now we are going to discuss thermal state of the field, which would be one of the more reasonable kind of state which we will be dealing with most of the time in the laboratory settings. In order to make concrete predictions, it will be good to have an idea how fields which very frequently could be described by a thermally populated field should behave in terms of expectations and correlations. So now, as we know from quantum mechanics, that the thermal state of any quantum system cannot be described by a pure state. It has to be a mixed state. So therefore, it has to be described by a density matrix. Okay, so that would be true for any quantum system. Therefore, this is true for our field as well. And as we know, our field is constituting of individual oscillators in Fourier domain. So therefore, I can think of that each Fourier mode K, which is like an oscillator, has a thermal density matrix description if the whole field is in the thermal state. So the kth mode oscillator state is being described by this density matrix, which is e to the power minus beta hk, which is the thermal density matrix of the system. Okay, the full field theoretic computations of this would be the rho, which is effectively collection of all the oscillators put together. So it would be e to the power minus beta hk1, e to the power minus beta hk2, e to the power minus beta hk3. Each hk1, hk2, hk3 is the individual Fourier Hamiltonian, which we have discussed about, which is made up of ak and ak dagger. Okay, but we also know all AKs and AK daggers, they talk to each other only for the same AK, meaning AK and AK dagger commutation is non-zero only for the same case. If I talk about different AKs and different AK daggers, AK with AK dagger or AK with AK prime, commutation is always zero. So therefore, I can club this product into summation over the argument in the exponential, such that the Hamiltonian operator appearing over here is commuting with each other. So ultimately, the full density matrix of the whole system is integration over d3k and hk, each individual Fourier modes Hamiltonian itself. Collectively, the whole thing which is appearing in the exponent is nothing but the total Hamiltonian of the system, and therefore there we have a consistent definition of the full thermal density matrix of the whole quantum field, e to the power minus beta h. Okay, which is general to any quantum systems or any even classical. So density matrix effectively can describe a classical ensemble of particles as well. So in that sense, any generic system which is thermalized can be described by a density matrix of this kind of thing, this kind of expression. Now we also know, given a density matrix, how to compute things out of it. That is to know what are the expectation values, what are the probabilities of finding some things, and that is obtained by taking the operator in consideration. Its thermal expectation will be the trace of the operator times the density matrix divided by the normalization of the density matrix. Okay, since this is our density matrix which we are writing in a thermal base, this sometimes the downstairs which is coming about should be a function of temperature as well, z of beta. Sometimes this is given a name path integral as well in the quantum field theoretic discussion session, but this is just the partition function of the system if you are tailored to think along that line. Notwithstanding what you want to call it, the definition of z is nothing but the trace of e to the power minus beta h. That is, if I project this operator in all the possible good quantum bases of the whole quantum field, then sum over all those basis elements, the trace would be that. Now we know quantum field is made up of vacuum state, let us say, where all Fourier modes are in their respective vacuum, or let us say one of them is in excited state. So let us say 1k would be just all other momenta is grounded, only one of the momenta, let us say k naught, that is excited singly. Similarly, there can be twice excitation in the same k naught, which is equivalent to every other thing in vacuum and twice excitation in k naught. Or I can have a 1k naught and another 3 particles at k naught primed. That means only around this pair I have particles and all other things are in vacuum. So in principle, different excitations in different k modes constitute a full basis for the description of a field. Field could be either found with some probability in vacuum or in one particle excited state, which one particle excited state, two particles excited state, which two particle excited state, and so on. So ultimately, a good complete basis of the description of a field is this collection Nk. This set Nk tells me how many particles are excited in which momentum mode. Okay, and this is a basis element. There are infinite dimensional space because infinite many possibilities are there for bosonic systems. Each mode can be populated from 0 to infinity. So therefore, there are infinitely number of basis element, and each basis element can be covered by one collection of Nk. Okay, so therefore, when I'm supposed to do this trace of e to the power minus beta h, at the end of the day, I should be doing summation over all possible distributions of Nk varying from 0 to infinity in all possible cases, and then put that along the density matrix, squeeze the density matrix along that, and that is giving me the partition function or the path integral of this. We have not discussed the covariant approach of the field, so I should refrain from calling it path integral in Euclidean basis. But anyway, there is a colloquial name people come up about with this. So now, as we discussed, this kit collection of n is ultimately telling me how many particles in mode k1, how many particles in mode k2, and this can be different. It can be 0, this can be 5, this can be 7, any arbitrary collection. This is one such element. So ultimately, that one such element can be put as a product over k and k. This is just a representation of that. Now, this partition function is known, and how to obtain any operator's expectation is known through the trace of operator times the density matrix divided by the partition function. So let us go ahead and compute the expectation value of the Hamiltonian itself. So in this process, the Hamiltonian will ride along with the density matrix divided by z, and the trace of the whole thing would be taken. Again, as we discussed, trace means put the basis elements on both sides and sum over all the possibilities of the basis element. This sum is happening for different possibilities of writing this Nk. Okay. So now let us see, there are two kind of terms appearing. One term is over here and one term is over here. So if I compute this object and I compute this object, then the overlap of these two things gives me the whole expectation of Hamiltonian in this density matrix. So let's just do it side by side. So first I want to compute this object. This object can be obtained from the dagger of Hamiltonian operator on Nk. If I take the whole thing and do the dagger of this, since Hamiltonian is a Hermitian operator, it will come back to itself. The ket will become the bra, and I will get a h. So therefore, I obtain this, take the dagger of this, whatever I get would be my first element appearing over here. So let us try to do that. So I compute Hamiltonian's actions on Nk. Remember, Hamiltonian, in the normalized Hamiltonian we will be talking about, we have thrown away the vacuum part which was divergent. The Hamiltonian is written as d3k, omega k, and nk. So that is what I have supplied over here. This operator, number operator, hits this, and then we get what it is. So first, this nk operator, which was ak dagger ak, this is true for a particular k. So this operator will search in this ket meaning this whole distribution. This whole distribution over here is the full state set Nk. So when Hamiltonian is operating, that means AK dagger AK number operator will hit this ket of collection of N. It will search for its own K value. Somewhere along the line, Nk will be here. And how many particles are excited in that K mode will come out. So that is the Nk. And omega K is already there from the definition of Hamiltonian. So number operator goes and plucks out the excited number of particles in that particular mode, and then you integrate over all the modes. So this is as simple as that. So action of Hamiltonian on this gives you back, this is an eigenstate of the Hamiltonian with this eigenvalue. Okay, if this is eigenstate of the Hamiltonian, we are familiar by now that exponentials of Hamiltonian will also be operator whose eigenstates are Nk. So you can find it to work it out that if this is eigenstate of H, it is also eigenstate of e to the power minus beta H. So wherever H operator is appearing, this summation d3k integration d3k nk omega k will appear, and the state will be back to me. Okay, so these two terms appear in my description of the expectation of S. Now I know what is this, I know what is this, what I have to do, take the overlap of these two outcomes. All right, so we take the overlap, divide by this partition function to get the whole expectation values. So I have from the left side coming as this thing's dagger. So this is real number, this is real number, this integration is over real number. So this remains intact. Only thing happens, this nk will convert itself into ket of collection of nk. Okay, and this will go ahead and hit this operator over here, this operator whose eigenvalue equation is this. So this will go ahead and hit this. Everything on the right hand side of the second term is also now number, no operator. So this nk will go all across to this and hit it over there. Nk overlap will come about. So ultimately you will get this nk overlap here, and all the remaining eigenvalues coming intact like they are. Here again, I have decided to write down this e to the power minus beta integration of d3k nk omega k as product of k e to the power minus beta nk omega k, because from there itself this product form appeared. The product form was converted into integration in the exponential. Remember here, when I wrote down the total Hamiltonian, that total Hamiltonian of this thing which had appeared on the top was just the single Hamiltonian put together too many times. The product became this integration. So that is what I have rewritten again. This is same as e to the power minus beta integration d3k n k omega k. Okay, so I have just rewritten it conveniently. All right. So if that is the case, then there is a z beta which is in the downstairs. Remember, z beta was what? Z beta was e to the power minus beta h squeezed between nk and k. So I will use this term, squeeze it between nks. So again, I will get the same thing back, and nk overlap. So z therefore is just e to the power minus beta nk omega k and product over k, the way I have written, and then nk, this nn overlap. So whatever nn overlap which is appearing in the top gets exactly cancelled from nn overlap appearing in the bottom, and in the bottom I am left with this finite piece only. So the normalizations are taken care of. From now on, I am just writing z beta as this quantity. Full z beta is this quantity product form times this object. But this object in the denominator is also present, in the numerator is also present, so I will not write it just for cancellation. So for the time being, I'm going to use the definition of z beta only up to this. You can think of the way that it is normalized state. So this might be 1, but not quite, because we have seen that single particle excited state is not a normalizable state. Two particle excited state is not a normalizable state in quantum field theory. So these are not made up from normalizable states. So this is not 1 in principle to speak with. But whatever appears as this in the numerator, which is potentially divergent term, there is an equally divergent term in the denominator. They cancel each other exactly, and we are left with a finite piece. That finite piece I am writing over here. Okay. Now thereafter, this is just plain manipulations of things which are appearing over here. Remember, what are we supposed to do? We have to trace. We have to do trace means summing over all the possibilities. So that means I have to sum over all the bracket of nk, possible set of nk, and here one of the nk is appearing, and all other k's are appearing as a multiplication over here. So there are various nks which are appearing, and there is a single nk which is appearing over here in some sense. So I can call it k prime if you wish, such that to distinguish it up against this single nk which is appearing over here. Okay, but no matter that, either I can break this integral k and this summation over nk. So this will be summation, this product means e to the power minus beta omega k1 n1 nk1 plus times e to the power minus beta omega k2 and k2, and similarly all the exponentials. And then there is a summation of all possibilities of nk1 being from 0 to infinity, nk2 running from 0 to infinity, nk3 running from 0 to infinity, and so on. And this whole collection space of possibility is collectively written over this over here. So what we can do, we can write the whole thing as this term. Here, this has gone like this. One of nk was surviving, which has appeared over here. The omega k I am writing over here. And this series sum I am writing in the expanded form like that. That's all. Now see what is happening. This is a particular mode k. And that particular mode k has to change according to the integration. Okay, but for the moment, fix this, that there is first a single mode k, and then you see all nks are appearing. So I should write down, this is e to the power minus beta. I have missed out here, so let me correct it this way, that here all other e to the power minus beta omega k primed and k primed are also appearing as a product. Let us say k prime, not summation. So let me write it cleanly once more in the usual color as well, so that it becomes part of the note. So it is e product over k primed, which is not equal to k, and e to the power minus beta omega k primed and k primed. So what does it do? All this k prime, which we had decided to call it like that, are appeared here. One of the term, which is just k primed is equal to k, I have plucked out, I have written over here. So the whole product over here is just this, in which one term I have just isolated and brought it to the fold of nk omega k. All other things are left over here. Okay, so this is how I have written. So let me clean it up so that it is visible more carefully. So now we have to just sit tight and see what happens out of this algebra. So we go to the next step. The single k, which is appearing as nk here and e to the power minus beta and omega k, that single k has to be summed over for different possibilities of nk. Remember, the series summations which was broken into parts will also contain a particular nk which I am talking about, this k. So that summation I have separated, and all other things whose individual summation is supposed to be present is being done like this. So this times this is equivalent to this, I'm claiming, and the remaining term over here is equivalent to this. This times this is here, and the remaining summation times this is appearing over here. So this is just the reorganization of the things which we have written. Okay, nothing profound about it. Now you see what kind of structure has appeared. There are so many summations of exponential of something kind, all k primed but for one. Only one k is not put in this product. That k has appeared here, and it has got multiplied with an extra nk and omega k actually. But apart from this k, all other k's are written as exponential, and exponential's argument is changing in integer steps. This we have done so many times in statistical mechanics, if you have done a course on. So this can readily be written individually. This is the GP, geometric progression. The first term starting from 0 will be 1, then e to the power minus beta omega, then e to the power minus 2 beta omega, and all the way up to infinity. And that summation can be written as 1 over 1 minus the common difference, e to the power minus beta omega k. So this is true for all k primes not equal to k. Okay, this is this. So this product I know becomes this. But about downstairs, the z beta is appearing. Z beta we know is just e to the power minus beta omega k nk product over k, and then all the possible nks. So this is exactly the same kind of computation, but this time it involves even this k which we had separated out. So this z of beta is exactly the same thing, with the factor that k appearing over here involves all the values. It does not leave out anything. This part here leaves out one mode. Which mode? That is being summed over. I have to first do k is equal to k1, put this thing, separate out k1, put it here, and evaluate that. Plus, the second term will be d3k integral, this suggesting the k will change the value. This function will change the value to k2. So k2 will be plucked out. The product form will have everything apart from k2 and so on. But in the partition function which is appearing downstairs, nothing is left out. The whole e to the power minus beta hk is undergoing the squeezing along with nk from both sides. So ultimately, you can convince yourself the partition function has all the e to 1 minus e to the power minus beta omega k. Here I have all the 1 minus e to the power minus beta omega k prime up to a single k which was plucked out, which is appearing over here because an extra nk came along with that. But in partition function, I do not have that. I only have to obtain the exponential Hamiltonian expectation value, which will exactly give me this. Now what up? So the two things we have computed this quantity, we have computed the partition function. So we should compute whatever is appearing over here as well, which is here I have written. You can quickly see this is nothing but del upon del beta of minus of del upon del beta of this nk e to the power minus beta k beta nk omega k. That means if I take the derivative with respect to minus beta, I will get down nk omega k and it will exactly become this quantity. And this summation I know how to compute. We have computed 3 times now, here, and once more. So you will get this. So that means I have to do a derivative of the whole quantity here with respect to del beta with a minus sign. You do that, you will get omega k e to the power minus beta omega k in the numerator and 1 minus e to the power minus beta omega k whole square. This is appearing in the downstairs whole square of that, and the exponential minus exponential derivative go on the top, which is this, which can be separated neatly as this factor and 1 over e to the power minus e beta omega. Okay, which you can convince yourself this is equal to that. Now you see what happens in the upstairs. In the upstairs, this term was providing structures like this, and only one k was missing in this. That k missing piece is supplied by this summation as a factor. So overall, this along with this become exactly equal to z beta, and they cancel each other. So z beta in the downstairs, full contribution from the second term and one of the term coming from the first term exactly cancel out each other. So I'm left with only the reminiscent piece which is over here. So you see, this is what I have written downstairs. This is this coming from the one piece. K not equal to k primed is already supplied. Put together everything. This is z beta, and they cancel each other. So I'm left with only the first quantity over here. So Hamiltonian expectation is d3k omega k e to the power beta omega k minus 1. So this is a useful number. This is a useful result which we have. It looks like it is summation over h bar omega k. H bar is there. I am writing in the unit of h bar is equal to 1. So energy of oscillators, but with number expectation 1 over e to the power beta k minus 1. So this looks like Hamiltonian operator was supposed to be number operator times omega k, number expectation operator times omega k integration over this way. So therefore it looks like that each individual mode is populated with these many particles at temperature beta and frequency omega k. All right. So having obtained the expectation value of the Hamiltonian, let us now go forward and see what is the field expectation value in the thermal state itself. Recall, in vacuum state, field expectation value turned out to be 0. In coherent state, it became a function of alpha k, the coherent state parameter. Coherent state parameter alpha k e to the power minus I omega kt divided by root 2 omega. The Fourier transform of this quantity told me what should be the field expectation. So the parameter of the state decided what is the expectation. Is this true for thermal state as well? The parameter of interest for thermal state is the temperature, beta. Beta is, if you remember, I have not defined it, but I am hoping that you are familiar with the beta. Beta is 1 over kBT. So this temperature sets your beta, and that beta hopefully will set the expectation value of the field as well. For Hamiltonian, it indeed has set up the expectation value of the Hamiltonian, which is this much. Whether this will set the expectation value of the field or as well, that we should compute. Again, By the definition of expectation of the field, we should be calculating the trace of phi times rho. That means I should put this quantity phi times rho being e to the power minus beta h, in the diagonal basis or the eigenbasis of the system, complete basis of the system, and divided by the partition function z beta. That is the standard definition we keep using. So this is the operator method, and we will write down the field in its mode and the AK and AK dagger like we have been doing all along. So let us write down first what is this. Why are we computing phi acting on NK? The same thing. I would want this part to be evaluated first, this part to be evaluated first, take the overlap, compute the sum. That is the game which we played for Hamiltonian. Previously, the Hamiltonian was sitting over here, and this time a phi is sitting here. So let us compute what is phi acting on NK, and then I will take the dagger of the whole equation. If phi is a real scalar field, that means it is Hermitian conjugate is the same as itself. So therefore, when I take the dagger, it will get back to itself, and NK ket will become NK bra like before. So let us do this. I take the expansion of the field in terms of mode function and the ladder operator, which is this. The operators are only AK and AK dagger. AK dagger will hit this state and make it search for its own K value across this whole decomposition. This, remember, it means NK1, NK2. So there will be some NK here, then other NKM, and so on. So this AK dagger will search for its label. It will find NK particle in it. Operation of that will make root NK plus 1 coming out, and the NK becomes NK plus 1. So AK dagger will raise the particle content in mode K by 1. Similarly, AK operator will hit this state, search for its own K, and decrease the number of excitation in that state by 1, NK minus 1, and root NK will come out as the factor. This is the usual ladder operators business. So therefore, phi K acting, phi X acting on NK is integration of this quantity times this e to the power ik dot x will come along with root nk and nk minus 1 in the kth mode. And the second term will come out with e to the power minus ik dot x here. And this will come along with root nk plus 1 with nk plus 1 particle in the kth mode. So I have obtained what is this? E to the power minus beta h nk we have already obtained in the previous computation of Hamiltonian expectation. We had already computed this quantity here. E to the power minus beta h. Again, let us clean it up so that we can see it with clarity. The last line of this page is the computation which we are after. So I'll just repeat, copy this and put it over here. So e to the power minus beta hk is known to me. What is left? Now let us take the overlap between these two. If I do this overlap, I will take the dagger of the whole thing. If I take the dagger of the whole thing, this will become e to the power minus ikx. This will become e to the power plus ikx. Root nk will remain root nk. This will remain root nk plus 1. And only thing changing will be this will become bra operators. So ultimately you can see, if I take the dagger of the first box and contract it or take inner product with respect to the second box, what I will get? All the stars of this left hand side, which will appear with e to the power minus ikx root nk, and this will have an overlap between this nk, which is being written as nk1, nk2, nk3, and so on, and bra of this, which is nk1, nk2, and only in the kth mode I have a k minus 1 particle, nk minus 1 particle. Similarly, for the second term, this exponential will become e to the power plus ikx, and e to the power minus beta, this thing will come out. Root nk plus 1 will remain root nk plus 1. This will become a bra, and that will hit this. So I have a nk1, nk plus 1 this time in the bra, and nkn. And right hand side, it is just this nk. Now you see, I have a structure. Two kind of terms are appearing in the expectations. One term is coming with the overlap of set nk with almost the set nk, only the one particular mode has one less particle. Similarly, The second term is right hand side, the ket of the system is set nk, and the bra of the system is almost the set nk, but one of the mode has one extra particle. So we need to compute these two things, supply over here, and then get done with the summation. However, we can see this can be written as nk1 ket, nk2 ket, similarly, and nkn set, and this will keep going on. And similarly here it is nk1 bra, nk2 bra. In between somewhere I have one extra particle in the kth mode, nk plus 1, and then all other things. So this nk1 will undergo contraction with nk1, this nk2 will undergo contraction with nk2, everything will go along. Only thing, nk here, which is appearing as nk particle, and from left hand side nk plus 1 particle, that overlap will happen. And similarly for the first term, nk minus 1 and nk overlap will happen. One particular mode inner product like this will appear, all other modes will have the same ket and bra. And this is fairly easy exercise to prove that if I start with a ket nk and take its overlap with respect to nk minus 1 or nk plus 1, both the cases, the overlap is 0. So that means this is 0 as well as this first term is 0. So therefore nothing survives in this computation, and the field expectation in the thermal state becomes identically 0. This is an exercise which is a fairly simple exercise. You should be able to prove even for harmonic oscillators. Different eigenstates of Hamiltonian are orthogonal, as simple as that. So therefore you see, like vacuum state, the expectation of the field is 0 in this state as well. But we know this is not an empty state because it is filled with particles. And how many? These many particles. Number expectation we have just written, these many particles in kth mode. The distribution is such that ultimately when get to obtain the field expectation, it sums up to 0. But that does not constitute it a empty field. In the next discussion session, we will start looking at how much of a correlation it has. Vacuum state also was mean 0 or expectation 0 object, but it had a non-zero correlations, thermal fluctuation, non-zero fluctuation, vacuum fluctuations. What about thermal fluctuation? Are they identical to vacuum fluctuation, or they have more robust structure? That we will discuss in the next class.